obviously analytical method is not applicable. After that, we actually saw advantages and disadvantages of CSE method, and actually there we represented our single natural finite system in the form of ESE, right? Finally, we saw that this is actually the ESE criteria for stability. That means this is actually the area, right? So the area under the power angle curve. So this is the Equilibrium criteria for stability. Then actually we actually completed this slide, right? Where actually we covered from the journey from A to B, right? Covered the journey from A to B. So again, I want to give a recap from here. So this is the power angle graph, P versus delta. Okay. Let's say the initial point is A, right? The initial operating point is at A. So at A, the mechanical input power PM0 and PE0 both are same, right? So if these two are same, using the swing equation formula, this difference will be zero. That means we will not get any acceleration in the rotor. That means the rotor will rotate at the synchronous speed. That means it is a steady state case, right? That's why in this point, so if I just write the associated parameters at point A, then it will be at point A. Okay. At point A, our PE0 equal to PM0, right? Then whatever the rotor angle we got at point A, we termed it as delta naught, right? This is the delta naught, and the speed of the rotor was termed as the omega naught, right? In this case, and this obviously this omega naught is the synchronous speed. It should be equal to omega s, the synchronous speed. Okay. Then at point B, from this point A, we applied some disturbance in terms of the mechanical input power, right? That means we increased the mechanical input power by a small amount. Now after some kind of increment, the new mechanical input power will be PM1, and obviously it will be the upward side from the previous PM0, right? So look, this horizontal curve is the PM1. Now whenever the PM1 will be higher than the PE, right, the electric output power, then from this swing equation we can say that the acceleration will be V star will be positive, right? This will be positive. That means rotor will accelerate, right? The rotor will accelerate. Rotor acceleration means obviously now in this journey our omega, that is the rotor speed, will be higher than omega naught, right? The previous omega. Have you understood this thing? Okay. If this is the case, then obviously our delta will increase, right? Delta will increase because okay. So, there is one thing that I want to just make clear that what is actually the delta and omega. Okay. Let's say let's come down. You may think that actually, as you know that omega is equal to d delta over dt, right? So we may think that whenever the omega is positive, that means the delta should be increasing, right? And whenever this omega is negative, the delta term should be decreasing. But this relationship is not that much straightforward. Why? Actually, this is not the correct way to represent this we are measuring our rotor position, right? That is the delta. Let's forget about this delta because we have already converted this mechanical quantity into the electrical. So the angular difference between rotor and the synchronous rotating frame will be the delta, right? So this speed always omega x and this speed is omega. So at the steady state, this omega and omega s will be same. At that time, there will be no change in the delta, right? Delta will be fixed. Okay. Now, if this omega, the rotor speed, is higher than the synchronous speed, then what will happen to delta? And anyone say? This delta will increase, right? Because look, let's say this speed is fixed at 314 radian per second. If we take 60 Hz or 50 Hz as our frequency, maybe we will get omega equals to twice pi f as this one, right? 314 radian per second. But let's say now it is 320. So this speed is higher. So over the time, this gap will increase, right? That means the delta will increase. Okay. Now let's think about the reverse case. Let's say attention. Now it is 320. Now it is again decreasing. Okay. And it is coming to 340. Okay. In this range, it is decreasing. Decreasing is from 320 to 340, right? Now in this case, what will be the scenario? Again, that in this case also, the delta will. Okay, I am asking the question again. That means, let's say for the first 5 seconds, this is 320 and this is 340, right? So the delta is increasing over that time. Now let's say after 5 seconds, this omega starts to decrease gradually. Let's say 320, 319, like this. Okay. Now what will happen to delta? Let's stop changing. Will it increase or decrease? Stop changing. Yeah? No. Look, this is still 314. But after decreasing, maybe this is 319, 318, which is still higher than 314, right? So obviously at that time also the delta will increase, right? Everyone understand this thing? So though we can see that the omega is decreasing, but delta is increasing. Why? Because the relative motion, we have to look at this expression. Whenever this relative motion is positive, at that time the delta will increase. Let's say at certain moment it is 340, the rotor speed. Also it is 340. So now the delta will be fixed over that time. Then if it decreases from this value, let's say 3 to 12, then this speed is low, this speed is high. So this synchronous rotating frame will try to catch this thing, right? And again the delta will increase. Okay, advantage of this thing. So that means always we have to look at this expression. If the relative motion between the rotor and the synchronous speed is positive, at that time the delta will increase, and if it is negative, the delta will decrease. Okay. And have you understood this thing? Because this will be needed whenever we will plot some figure. And you will see that your delta is decreasing, but your omega is decreasing, but your delta is increasing. Okay. So in that time you will ask the question, sir, how is it possible that omega, the speed is decreasing, but the delta is increasing? But have you got the idea? So we have to look at this expression.
Sir, delta की gradually decrease होता है
Okay. Look, what is delta? Delta is the angular position between these, right? So let's say this is 314. This speed is fixed, right? So it is always rotating at 340. Previously, the highest value of this rotor speed was 320. Now let's see it starts to decrease, right? Now let's see it is 319, 318, but these values are still higher than this 314, right? So this speed is still higher. And this delta will also increase, but that increase will be at a the change will be smaller, right? But also at this stage the delta will be increasing. Okay. Maybe the increasing rate will be smaller, but the delta will increase. Okay. And now let's go to our main slide. Now here, okay, so now we have increased the PM PM1 is higher than PE, so there will be acceleration in the rotor motor. That means the omega value will be higher than the synchronous speed. So the delta will be increasing, right? Because that means the relative speed between these two will be positive. So delta will increase over the time. Okay, that will be the case. Then if delta increases, we know that the PE is actually some kind of function of the delta, right? Sine function of delta. That is the PE is P max sine delta. So if delta increases, the PE value also increases, right? So that's why from this A, the journey will be in this path from A to B, using this power angle curve, this journey, right? Because in this journey, the delta is increasing, also the PE is increasing. Then at point B, we can see that actually the PM and PE are now equal, right? Well, means according to this swing equation, we should get no acceleration here, right? No acceleration here. Now we actually came into this point, and whenever we are at point B, we can see that there are some stored kinetic energy inside the rotor, right? And that energy is this area ACB. And how did we calculate? We calculate using this formula, right? So the area under this curve. So this is actually the PM1 minus this thing will be the PE, right? So PM1 minus PE is the P max sine delta. And what will be the range of this delta? It will be from delta naught to delta 1, right? Then we have to integrate it with respect to delta. Then we will get the area of ABC, right? And this area is termed as A1. So we covered up to this in the last class, right? Okay, now let's go from this point. Our journey is not yet finished. Okay. So now here in this point, again the PM1. So at point B, okay. So here this point is actually from A to B. Okay. So this is actually the journey of A to B. This is the scenario. Okay. And now at point B, we can see that the PM1 is equal to PE, right? So if in the swing equation, this acceleration should be 0, right? So before that, let me draw the omega versus T curve, and this is the omega versus T, and this is, let's say, delta versus T. Okay. So let me plot this two curve so that you can understand these both the points clearly. Okay. So at the initial stage, at this point A, what was the speed? Omega naught, right? Let's say this is the speed omega naught. Okay. So this is, let's say, at line T equals to 0. Okay. So in this duration, the system was in the steady state. That's why the omega is omega naught, right? Then this is actually point A. This is point A. So up to point A, the journey will be omega naught. Then we increase the PM. Okay. So from A to B, the omega value will be higher than this omega naught, right? Because there will be acceleration, right? So what will be the change? It will be like this. Okay. And it will come to this B. This point is B. Because look, now the omega, this is actually the omega. Over the time, it will increase from A to B, right? So this will be the change here. Now look at the delta versus T curve. Here again, this is the initial stage. What was the initial value of delta? It was delta naught, right? So this is actually the delta naught. Then from A to B, what will happen to this delta naught? It will increase, right? From A to B, it will increase from delta naught to delta 1. So also it will increase like this. That's it. This, okay. Yes. This is point B. And what is this value? This is actually the delta naught. Okay. This is delta naught. Okay. Now point B. Okay, now we are at point B. So at point B, PM1 is equal to PE, right? So using the swing equation, the acceleration should be 0, right? Acceleration 0 means the rotor will rotate at synchronous speed again, right? That means the rotor speed omega should be omega s. But at point B, what was the value of this omega? It was higher than omega naught, right? Can it be suddenly omega naught? Can this jump be suddenly like this? No, right? Because there is some inertia, and most importantly, there is some kinetic energy stored here, right? So due to this energy and due to the inertia, this omega can't suddenly change from this higher level of omega to the synchronous speed, right? It can't happen, right? So what it will do? It actually can follow this curve. Maybe now will come further, right? If it is the case, then also this delta will be higher. Why? Because the rotor is not yet coming to the synchronous speed. It is still higher than the synchronous speed. So the delta will still increasing, right? That means this delta will still increase like this. Okay? That means we are now in this region. Okay, have you understood? From this point, due to the inertia and due to this stored energy, we will go further, right? We will go further. And now the delta will increase means we have to go in this direction, right? We have to go in this direction. Now look at this area, this direction. Again, from this point B to let's say D, this is our journey. So in this point again, what is the relationship between the PE and PM1 here in this journey B to D? PE is higher, right? PE is higher. Okay. So PE is higher means using this equation, what will be the value of d square delta over dt square? It will be negative. Negative means the rotor will decelerate, right? So rotor deceleration means this omega value will now try to reduce, right? It will try to reduce, and it will try to reduce, and at certain moment it will come here. It will come to exactly omega, right? And up to this, whenever the omega is decreasing, but still it is higher than this omega naught, in this time this delta will also increase, right? Have you understood this phenomenon? Because here in this region, though we can see that the omega is decreasing, but this omega minus omega naught is still positive, right? The relative speed is positive. So this delta will still increase, okay? And it will come to this G, where actually this G, where again this omega will take the omega naught. And we don't know this G point, right? Let's say this is one arbitrary point. At point G, we are getting again this omega as the omega naught, the synchronous speed. And at that time, this delta is this point. Okay, so this is, let's say, our at T. Okay, this is at T. So at T, what is the value of delta? This is the delta max, right? This is the delta max. Why this is called delta max? You will understand it a little bit later. Okay. So now this point is delta max. Okay, this is delta max. Okay. Now we are at point G. Okay. Now this G point will be such that all our stored kinetic energy that was stored during the acceleration phase will be given back in the deceleration phase. So this phase is actually the deceleration phase, right? Because in this region ACB, or from A to B, the rotor actually accelerates, right? But from B to D, the rotor decelerates, right? So this energy, the ACB, this area actually was stored during the acceleration phase, and now in this deceleration region, this energy is given back to the system, right? So that means these two areas should be equal. Okay, that means the area ACB should be equal to area BDE. Okay, that is area A2. Now, using the formula, can you write the area A2? How can you write this area A2? A2, the integration term. What will be the area A2? again it will be look P minus PM1, right? Because here P is higher, right? Or we can take the same thing as this PM1 minus P max sin delta, but this time the delta upper limit and lower limit will be different. What will be the lower limit? It will be delta 1, and what will be the higher limit? It will be delta max, right? And it should integrate it with respect to delta. And this later we will get some minus 1, right? Minus area. And you can take the modulus of it. So minus area means this is actually the deceleration phase, deceleration area. And this positive area means the acceleration area. That's why you can use the same expression here. Okay? Though you know that you will get the minus, but minus means the deceleration area. Okay? And obviously these two area should be same, right? That's why it is called the equal area criterion. Okay? This is called the equal area criterion. Have you understood this thing? Okay, now if I just give a small recap. So from A to B, now just look at the omega versus T and delta versus T curve. Now I will just explain these two curves. Okay? From A to B, what was happened to the omega? It increased from the omega naught, right? That's why from A to B it is increasing. And if this omega increases, then also the delta will increase, right? Because the relative speed is here positive, this region, because this is omega naught. Once the omega value is higher than this omega naught, at that time this delta will increase. So this delta is increasing. So from this is point A, from A to B, this delta value is increasing from delta naught to delta 1. Then from B to D, at B, the PM1 and PE are exactly same. So again this should be the case, right? The omega value should come to the synchronous speed of at omega naught, but it can't come suddenly, right? Rather it will come gradually. So whenever it will travel across this path, so across this path also this omega is higher than omega naught, so the delta will still increase. And delta increase means we will go in this direction, right? From delta 1 to delta next direction. That means the curve will follow this thing, this horizontal curve. Now we are here, right? And it will come to this delta max, so that this area is due to the deceleration, because in this area P to T the deceleration is occurring. So this is the deceleration area, and previously it was the acceleration area. Okay? So these two areas should be same. Okay? And this is called the equal area criterion. Have you understood this thing?
So is the delta versus T curve is it straight line or
Okay, no, this is not actually the straight line. It will kind of sinusoidal now. Okay, so it will change sinusoidal. So it will change sinusoidal. Okay. Do we have any question up to now? Now, actually, we are not finished yet. We have some more discussions here. But before that, do you have any question here?
So why it should be sinusoidal?
I'm just taking it as kind of this value, okay? You can take it like this, but here actually our point is to just understand that whether from A to B or del omega is increasing or not. Just look at this point, okay? No need to think about this thing. Okay? If you whenever we will solve some problem, we will see that why this will just kind of sinusoidal. Because in the expression of this, there will be some sine term, okay? That's why it will be sinusoidal. Okay? We will see that thing later on. Also in the last slide, whenever we solved example 11.2 and we plotted delta versus T and frequency versus T, right? We saw some sinusoidal term, right? Why sinusoidal? Because there was some sine term inside the solution, right? So here the same. But the only understanding from this slide you will need that whether in this region the delta is increasing or the omega is increasing or not. Now look at point T. At point T, now we are at point T. So all the stored kinetic energy that was stored during this stage has completely given back to this system, right? So the system can go further, right? It will be here. Okay. Now look at point T. So at point T, so let's just move this writing. at point D, at point D, okay, what is the relationship between PE and PM? Now the PM is actually PM1 because we have increased our mechanical input power, right? What is the relationship at point D? This P is higher than PM1, right? If this is the case, by observing the swing equation, what will be the result of the acceleration? This term will it be positive or negative? It will be negative. Negative means the rotor will decelerate, right? That means this term, d square delta over dt square, this term will be negative. Negative means the rotor will decelerate. Decelerate means this omega, the rotor speed, will be less than omega naught. That is the synchronous speed, right? So after point T, what will be the scenario? This omega will go further below, right? Like this. Okay? Like this. That is this case. Okay. If this is the case, now can you say in this region what will happen to delta? Delta will increase or decrease? Delta will decrease. Delta will not decrease. Have you understood this thing? Because this is the main point here. So in this region, look, the relative speed is now negative. That means the delta will now decrease. Okay. Now delta decrease means along which path will be our next journey? Can anyone say? From now we are at T. So along which path should we go forward now? Along this path or this path? Along this path, right? Because the delta is decreasing means we have to come to the left side from delta S, right? So now again the journey will be from G to B. Okay. So this delta will decrease. So from here the delta will decrease. Okay. This delta will now also decrease. Delta decrease means again the journey will be from D to B. So let's say now the journey is from D to B. So the D to B, this journey, in this journey the PE is higher than PM. So there will be deceleration in the rotor body. Okay. That's why the delta is decreasing. But at point B again, look at point B. At point B again, this PM1 and this PE will be same, right? These two things will be same. Have you understood this thing? Again in this point, these two will be same. So now again we are at point B. So at point B, these two are again same. That means again the omega value should be equal to omega naught. But we are at already some lower value than this omega naught, right? So again it can't again jump suddenly from here to here. It can jump instantaneously. Rather it will actually take this point, right? This point. So from this below point, this is point B. After B, the omega will decrease, right? Omega will increase from this point. From T to B, the omega will decrease. Okay. Now from here at point B, the PM1 and PE both are equal. So the omega value should be this omega naught, but it can't get this omega naught value instantaneously. Rather, it can again increase its value. Okay, so that it can take this value at some moment, right? Now in this region, can anyone say? So that means we are here, and also this is point B. Okay, this is point B. So at point B, what will be the value of delta? It will be delta naught, right? So this delta term will be like this. So this is again point D, so that this delta value can be delta naught. Okay. Now from this point B, the omega is increasing, but this region, this value of omega is still lower than this omega naught, right? So what will happen to delta in this region? This delta in this region, it will still decrease, right? So that means it will still come here, okay? And it will come to this A again. Okay, that means in this region, in this backward journey, whatever energy that was stored due to the deceleration phase. Okay. Now in the acceleration phase, all of this energy will be given back. Okay. Now again, this delta, this system will come to point A. Point A is again this delta value will be in point A. This delta value will be delta naught, and in point A here the omega value will be omega naught. So this is point A, because at point A again the we are actually coming to this steady state case, right? Because the omega value is reaching to the omega naught value. Okay. Now have you understood this journey? This is A to B, B to D, again B to D, then B to A, right? Now from A, what will be the scenario? Now from A, we are here, right? We are here. Now still here at point A, what is the relationship between P and PM1? Because we don't have any PM0 now. We have increased it to PM1, right? What is the relationship between these two? The PM1 is there at point A. At point A, right? So due to this, there will be some acceleration again. So this omega will increase. Again, it will follow this curve. So this is for one complete cycle. So the rest of the cycles will be identical to its like this. Okay. And also this for this delta, it will be like this. The swing will be in between this delta max to delta naught, and this center point will be delta 1. Okay. So this swing will be like this. Like this. Okay. So again, it will be point B, it will be point D, it will be B again, it will be point A. That will be the cycle number 2. So this cycle will continue. Okay. Here it will also the same. Have you understood this thing? Now by looking at this curve is actually neither decaying nor growing over the time, right? It is continuously swinging between two fixed points. And this type of system is called marginally stable system, right? So this is the marginally stable. So in your small disturbance stability slide, we saw that whenever we got two poles along the y-axis, the system was marginally stable. Why the system is marginally stable? Because this is better than the unstable state, but obviously our target is to get the stable, purely stable state, right? But why we are not getting the purely stable state here? Can anyone say? You can recall the concept from the previous slide. Why didn't we get the purely stable state in the small disturbance stability slide in the first time? Because we didn't incorporate any damping, right? Whenever the damping effect comes into the action, at that time we get some kind of stable state, right? Here as well, we are not yet dealing with the damping, right? That's why it will be marginally stable case. Okay, and this type of oscillation is called sustained oscillation. Sustained oscillation. Okay, because this oscillation is neither growing nor decaying over the time. Have you understood this thing? Now let's move forward.
Sir, from point 0 to 8, our omega is
From 0 to 8. Actually, we have started our discussion from point A. From this point. This was our initial point. At point A, we considered that the PM0 and PME was same. That means there was no acceleration. The rotor was rotating at the synchronous speed. That was the steady state case, the initial case. And from this A point, we started our journey. Okay.
so sir, like omega naught, delta naught, they will start from a straight
Yeah.
line and then
Yeah, exactly. This point, this is the initial stage, right? Let's say this point remains, let's say for 5 seconds. So this is the t not will be 5 seconds. So from 0 to 5 seconds, this omega value will be fixed at omega. Also the delta value will be fixed. Okay, that's why there will be some straight line into some fast initial moment, and then the system will oscillate. Okay. Now in the next few slides, you will see the same things. Whatever I have discussed, all the things are written over here. Okay. Okay. All the things good. This is the area 1 and area 2 should be equal. Then this is the thing. Okay. Look. point D, right? So from A to B, what will be the case? The omega will be higher than omega naught, right? And from B to D, it is still higher than omega naught, right? Because our curve was like this. It was like this. Okay. So this is the curve for omega, omega versus T. So this is A, this is B, this is D, this is again B, and this is A, right? So from A to B, the omega is higher than omega naught. Okay. From B to D, the omega is decreasing, but still here this is omega naught, so the omega is higher than the omega naught, right? Then the journey was in the backward direction. Now from B to D, the omega is less than omega naught, and from B to A, the omega is increasing. That means the road is accelerating, but still in this region the omega is less than omega naught, right? And obviously in point A and at point D, our omega is equal to omega naught. Okay. Everyone understood this thing? Okay. Now here you can see this is in terms of omega and this is in terms of acceleration. Okay. So in terms of acceleration, what will be the case? If I just redraw this, it will be like this, right? Time, this is omega. So this is omega naught. So this is point A, point B, point D, again point A, point B, right? So from A to B, what is the information about acceleration? The acceleration is positive, right? This is acceleration. Then from B to D, deceleration, right? That's why it is negative. Okay. Again from D to B, it is negative, right? Then from B to A, it is again positive. Okay. And obviously in these 2 points, there is no acceleration, right? There is no acceleration. This 2 points. Okay. Okay. Now this is the omega versus time curve. So if you want to see some kind of time domain response, okay. So this is for omega versus T. Okay. So this is our omega naught. Let's say 377. If you take 60 Hz as your frequency, then you will get omega naught as 377. Okay. So this is point A. So at point B, you will take the highest value, right? Let's say this is this thing. Let's say this point is 377.4. Okay. Then from D to T, it will again decrease, right? This D will be again equal to omega naught. Okay. Then from D to B, it will come some less value, and let's say it is 376.6, because this is marginally stable. So this will be the center point, and this omega versus T curve will be swinging back and forth continuously, right? So if in the upside the increment is 0.4, this is 377.4 and this is 377. In the below side, the difference should also be 0.4, right? That's why this is 376.6. Again, it will increase like this. Everyone understood this curve? Now, this is obviously without damping, right? We haven't incorporated the damping. Okay, now, what will be the scenario for delta versus time? Okay. Look for delta versus time. For delta versus time, what will be the initial value? Delta naught, right? That is at point A. At point B, it will be delta 1, and at point D, this is the delta max, right? Because this is the highest value that this delta can take in this journey, right? That's why this is called delta max. Again, from D to B, it will come to delta 1, then delta naught. So the swing will be in between delta max to delta naught, and what will be the average value of the center point? It will be delta 1, right? And in this case, what was the average value? It was the omega naught. Okay. Now there is one thing that you should remember from here, that whenever the system will be stable, let's say the system will be stable, So what will be the final value of this omega here? Can anyone say? If the system goes to the purely stable state, what will be the final value of omega? It will be omega naught, right? Let's say we have added the damping. So what will be the final value of omega after some oscillations? This 377. Or you can say that it will be omega naught, right? But what will be the final value of delta? Will it be delta naught? It will be actually delta naught, right? So it will take a new value. This is also called the stability, right? Because stability can be the previous value or it can be the new value. Okay. Now this is also without damping case. Now let's think about the with damping step. Okay. Now this is the curve for omega versus t and with damping. Okay. With damping. That means so if there is damping, okay. So what is the damping power? This is PD. Okay. PD and it is P the damping constant omega minus omega naught. This is the equation. Okay. And in linearized form, it will be let's say del PD equals to T del PD. Okay. That means this damping will act as your induction motor or induction machine effect. Right? We have discussed this thing in this stability. So in summary, this damping will try to reduce this gap omega minus omega naught. It will try to reduce this gap. Okay. That means whenever in this case always it is oscillating, right? It is marginally stable. But this gap is whenever there will be damping, this omega minus omega naught, this damping power will try to reduce this gap over the cycle. Okay? Have you understood this thing? That means if you go in this curve and if you think about the damping state, so from let's say A, we have started from A, then we have come to point B. So let's say this is the acceleration power, stored kinetic energy, right? Now from B to D, without damping it should come up to D. But if the damping effect comes into action, it will come a below value than this, because there will be some damping power. So it will come, let's say some G naught value that is below than this D. Okay. Then the next cycle it will be from T prime to B. Again it will not come to A, rather it will take a new value that is A naught, that is upper than this A. Okay. Then in the next cycle again from A naught to this D naught, D prime journey, it will not take the D prime, let's say it will take another small value, that will be D double prime. Then in the next journey it will take from D double prime to let's say A double prime, that will be again from here, right? So the swing will be like this, let's say it will be from here to here, okay, from A to D prime, again it's from D to some A prime, so the value is here less, right? Again it's from A prime to some small value of T, there is the D double prime, again from this D prime to A double prime, like this. So gradually the oscillation will decay, right? That's why the omega versus T curve you will see it like this. Okay. So whenever there will be some damping, you will see that. Okay. From it is starting from 377. So after few cycles, what is the final value? This is omega 377, right? And what will be the case for delta versus time? It will be look. It will start from this is our delta naught. Okay. This is the delta naught. And it will reach a high value. Again, finally, it will reach up to this value. And this is actually nothing but our delta 1, the center value, right? Any question up to now? Right? Okay. The same thing has been written over here. Okay. Okay. So this is actually a stable system. Okay. This is a stable system, and this is without damping. That's why it will marginally stable. And this is with damping. That's why this is the purely stable. Okay. And now let's think about the unstable state. What will be the unstable state? What can be the omega versus T curve? Both are the omega versus T curve. It can be two types. Either it will grow exponentially like this, or it will grow like this. in monotonic fashion. Monotonic means only in one direction, right? But here you can see sometimes it is increasing, then decreasing, again increasing like this. So this is exponential decay, exponential growth, and this is some kind of monotonic oscillation. Also for delta versus t, you will get the same thing. This is kind of exponential growth, and this is again the monotonic oscillation. Okay, delta versus t. Have you understood this thing? We will see this type of task whenever we will solve some problems. Okay, no problem. Now just I am giving you some recap how this system will work and what is meant by a stable system, unstable system, and marginally stable system. Then the next discussion is a new topic, and we will start this discussion in the next class. Okay, actually, okay, you didn't ask one question. That is, sir, let's say if we started from here, right? And we used the increment of PM1, let's say about this much, right? If you take your PM1 like this, what will be the scenario? You will get us, right? Or let's say you have taken PM1 like this. If this is your PM1, this is your PM1. Now if you take this PM1, now forget about this PM1, your PM1 is this. So from this you have taken the new PM1 here. So it will come from here. So this will be your kinetic energy stored in the acceleration phase, right? Now this same energy will be given back. So how it will give back? It have to travel from here to, it need to cross this pi by 2 boundary, right? So it will to come here. So, okay, yes. It will come to this state, and once it will fall this state, the system will be purely unstable. You will not again get back to the system. That is the unstable state. We will discuss these things, no problem. And when at that time we will see this type of curve. Okay, we will see this type of curve then. Okay. But we know that this is the unstable curve, right? But how we will get that unstable state? Like this. Okay. That's why you have to be careful to select this increment. You can take it so much, right? Because this is our steady state stability limit. We can't go beyond this limit, right? That is the case. Okay, so we will discuss this thing, no problem. We will see in some future slides that this will happen. Okay, look this. This is the higher PM1, right? So now this is your stored energy. So to actually give back this whole energy, you need to come up to this thing, right? And once you are here, you will get it. And from that discussion, you will find the stability limit. What will be your stability limit? Okay, that will get determined. Like this, okay. Then okay, then that will be another scenario. Maybe it will go in the over region. Okay. So we will discuss this thing only for the higher case. Okay. So these things will be discussed in